Good morning and good evening, everyone. My name is Sabah, and I am a senior researcher from Reckitt AAP. And today I am going to host this session of TrustML Young Scientist Seminar. But before that, let me allow me to briefly introduce Reckitt AAP to our valuable guests. So the full name is Reckitt AAP is Reckitt Center for Advanced Intelligence Projects. So the center was founded in 2016 as a research center for the Mixed AAP project. This research center is headed by Professor Madashi Sugiyama and conducts Japan's leading AI research. It aims to enhance AI fundamental technology and its real-world applications, and also encourage collaboration with various researchers and engineers in related fields. We'd be very happy if you could visit us in our Nihonbashi offices in Tokyo, so you're always welcome. And we started this TrustML seminars in January 2022, so now it's a bit more than 1 year. And just a quick reminder is that we are on the 54th, and even if we share the presentation online on YouTube, you still need to request the authorization from the authors to reuse any content. And especially for today, I'm very happy to welcome our guest, Dr. Zhen Fang from the University of Technology, Sydney. He's a research fellow at the Australian Artificial Intelligence Institute, working with Professor Jie Liu. He received his master's degree in pure mathematics from Xiamen University, 2017. And then he completed his PhD in 2022 under the supervision of Professor Jie Liu. His research mostly focuses on transfer learning, statistical learning theory, and auto-distribution learning, with major publications in top venues like NeurIPS ICML. And recently, his paper received the Outstanding Paper Award at NeurIPS 2022. And this is the talk that he is going to have today. So again, Dr. Fang, I'm very happy and very pleased to have you today. Thank you for joining us. And I will leave you the floor.
Hello, everyone. I'm Zhen Fang from the University of Technology, Sydney. And it's my honor to make a presentation in a trustworthy machine learning young scientist seminar. And today my topic is understanding generalized out-of-distribution detection and theoretical field. Now let's begin. Now here is a table of contents. Yeah. First, I will overview the structure of the presentation here. First, I will introduce what is generalized out-of-distribution detection. And in the second part, I will propose several challenges in theory of generalized out-of-distribution detection. Then I will introduce the work I've done about the learnability of generalized OD detection. And the fourth part will make some discussion, and last, I will summarize our results and introduce our future study. Okay. As Confucius has told us, no pretending to know what you actually don't know. So, the generalized OD detection aims to give AI the wisdom to distinguish what knowledge AI has learned and what knowledge AI doesn't know. So why does generalized OD detection matter? Here, I will use an example to show. In a figure, there's an older scientist and a robot. The scientist created a robot and taught the robot how to recognize animals. And one day, the robot says, "Father, I have learned how to recognize all kinds of animals. I think I have the ability to survive outdoors." That means the robot wants to go outdoors. And then the scientist gives the robot an issue. That is, the scientist shows a picture. In a picture, there's a tree. And ask the robot, "What is this?" Because the robot can only recognize animals and the tree, is very similar to snake. So the robot will say, it's easy, it's a snake with a very high confidence. Of course, it's not correct. Then, okay, the scientists say it's not an animal. Sorry, I cannot permit you go outside. So robot should have the ability to realize what it can do and what it cannot do. Here, I divide the generalized O detection into 4 similar directions. The first is one-class semantic anomaly detection. The second is one-class novel detection. The third is open-set recognition. And the last is OOD detection. The one-class semantic anomaly detection and the one-class novelty detection focus on the one-class cases. And in fact, these 2 directions are same or similar. And open-set recognition and OOD detection focus on the multi-class cases. And I think the most difference between open-set recognition and OOD detection is that the benchmarks they used are different. And in the classical OOD detection methods, they follow some unified framework. Okay. In a survey paper, generalized out-of-distribution detection, the author have listed the difference of these 4 directions. And if you are interested in it, you can see this survey paper for more details. And here, I will introduce a structural definition of generalized OOD detection. So first, we have some ID joint distributions, DXI, YI. And these ID joint distributions, we will obtain some labeled ID data, S. And by this labeled ID data, we can train a model or a predictor, H, from some hypothesis space, big H. And during the test type, we also have some OOD joint distributions. This is unsafe during training. And by the OOD joint distributions, we will obtain some OOD data. And the ID joint distribution and OOD joint distribution, they have disjoint label spaces. In the image tasks, that means ID distribution and OOD distributions, they have different semantics. So we expect that the predictor can detect the OOD data and classify the ID data well. Here, I will show an example to show the difference between the traditional supervised learning in classification and the traditional generalized OOD and the generalized OOD detection. In this figure, we say, in supervised learning, the training data and the test data, they show the same label size, such as the car, dog, people. However, in all generalized OOD detection, in the test time, there's another additional classes which is unknown, such as shark and dinosaurs. So OOD detection is a subtopic of the generalized OOD detection. And in image tasks, ID data and OOD data have different semantic meanings. The classical OOD detection algorithms follow unified framework. Here is the unified framework. G is the OOD detection predictor. And E is a score function. F is a deep model. So the score function, the input is the deep model. And if we give the output of the model into the score function, then we can obtain some score. We can use the score, to estimate whether it's ID or not OOD. If the score is larger than some threshold alpha, then the OD detection predictor will regard the data as ID. If the score is smaller than some threshold, then the predictor will regard this data as OD. So the classical OD detection depends on basic idea, that is, a good model F should have a good OD detection ability. What's the meaning of this? I will give an example to show it, such as if we fully understand what is a car, then we will know what is not a car. Here, so here I propose the first challenge in theory is that can we develop a theoretical framework to understand how good a model should be to ensure that it has a good detection ability. And for example, OD generalization model is a good model. And OD generalization aims to learn the semantics based on all kinds of different environments. So, my question is, can a good OD generalization model achieve a good OD detection? If we can address this issue, then we can bridge OD generalization and OD detection is two different directions. And the second challenge is related to the learnability of generalized OD detection. And this is the main topic in this talk. Why we need to study the learnability? You see, because in the real world, the OD data are infallible. And sometimes, maybe it's deficient. So we think that an effective OD detection algorithms should have a good generalization ability, that it can perform well on device OD data. And under some conditions, the learnability is equivalent to the exercise generalization analysis. And by researching learnability, we will know when OD detection can be generalized well in the real applications. So here is an example. In our lab, we often use CIFAR-10 as ID data to build our model. And in fact, we hope the OD detection model can perform well on all kinds of different OD data, such as the minister data, the sum, the iNaturalist. So here, I will introduce some necessary concepts. We use RID to present the ID risk with respect to predictor H. And in fact, the RID means the estimation of the risk for the predictor on the ID distribution. We use the ROD to present the OD risk with respect to the predictor H. And the ROD estimates the risk of the predictor and the OD distributions. And we also use alpha RID plus 1 minus alpha ROD to present the alpha risk. Why we use the alpha risk? The reason is that the imbalance issue in OD detection is one of the core challenges. So here we introduce a weight alpha to adjust the importance of ID and OD. Then the minimal alpha risk corresponding to the minimal alpha risk. A presents an OOD detection algorithm. And given the ID training data S, AS will select a predictor from the hypothesis space H. Okay, here I will give a strictly definition of the learnability of OOD, generalized OOD detection. Yeah, we hope find an algorithm A, and with high probability, we hope the alpha risk with respect to the predictor AS can approximate to the minimal alpha risk uniformly. In other words, based on finite ID training data S, we aim to select a predictor AS from some fixed hypothesis space H with approximate minimal alpha risk. And we expect the approximation to get better with the increase in data size. And we also expect the equation 1 can hold for diverse OOD detections uniformly. Okay. And in our work, is out of distribution detection learnable? Yeah, we answer the learnability of generalized OOD detection partly. And in our work, we realize only when the ID distributions and the OOD distributions meet some special conditions, the generalized OOD detection can be learnable. So let's begin from a simple observation. Here, is the equation 1. The left term is the alpha risk with respect to the predictor AS. The right term is the minimal alpha risk. Okay, we can find that the left term is a linear function with respect to the weight alpha, but the right term is a concave function with respect to the parameter alpha. So we hope a linear function can approximate to the concave function uniformly. That tells us the minimal alpha risk should also be a linear function with respect to the parameter alpha. So based on this, we proposed one of the most important conditions in our work, which is called the linear condition. Linear condition is a necessary condition to the learnability of OOD, generalized OOD detection. And it says that the minimal alpha risk should be a linear function with respect to alpha. And based on this linear condition, because it's a necessary condition, so if we can find some ID distribution and some OOD distribution such that the linear condition doesn't hold, then we can find for a non-trivial hypothesis space H, the learnability of OOD detection is not distribution free. What's the meaning of distribution free? That is, the learnability of OOD detection cannot hold for all ID distributions and all OOD distributions. Recall, we can remember that in a packet learning theory of supervised learning, the supervised learning is distribution free, but the OOD detection is not distribution free. So this is the largest difference between the packet learning theory of OOD detection and the supervised learning. Based on this simple observation, we proposed our own issues. We need to consider the learnability of generalized OOD detection in some special distribution spaces, which means of distribution spaces that is a space D, consists of some pairs of ID and OD distributions. And our aim is to answer that we want to discover the sufficient and necessary conditions to ensure the learnability of generalized OD detection in some practical distribution space. Yeah. We began our research from a simple toy distribution space, which is called a single distribution space. Yeah. This is a simplest space. That means the distribution space consists of only one pair of the ID and the OD distributions. That means the size of the distribution space is 1. And then we have proved that generalized OD detection is learnable in a single distribution space if and only if the linear condition holds. This is a very important resource in our work. Yeah, because our work depends on this theory. And this theory also tells us the linear condition is important. And if we want to develop more practical and deeper theories, we need based on these results. Okay, now here we began to extend these results for a more practical and deeper distribution space. Yeah, I call it the compact ID distribution space, which means that the compact distribution space, the ID, the joint distribution part, forms a compact set under some distribution matrix. So what is the compact set? Is a topology term. That means the set can always find the finite covers, by some open ball, And why I discuss the compact ID distribution space? Because it corresponds to many real cases. In real cases, we can only collect finite ID data sets, such as CIVA10, MNIST, SVHN, and ImageNet to build our model. So the finite ID data sets are the special cases of the compact ID distribution space. And then we need to extend the linear condition to a more general case, which is called the compatible condition. So first, I will introduce a new concept, which is called OD distribution set, DO. Which means that for two ID distribution DXI, YI, we collect all OD distributions DXO, YO, which can form the pair in a distribution set D. And all the OD distribution DXO, YO, forms an OD distribution set DO. And the compatible condition says that the linear condition can hold uniformly, for all OD distribution set, for all OD distributions in the OD distribution set of DO. In other words, the compatible condition tells us we can always find a consistent solution to distinguish ID distributions and all OD distributions in the corresponding OD distribution set DO. That means, the existence of OD detections, of a solution of OD detections. So then, based on this new concept, we propose our main theory. That is, generalized OD detection is learnable in the compact ID distribution space if and only if the compatible condition holds. And furthermore, under some suitable distribution metrics such as max-min discrepancy or versus time distance, we can prove that the convergence rate can arrive 1 over square n. And this resource can give us many real applications and help us to explain some phenomena in the experiments. Yeah, here I will show an example how to use this theorem. In the near-O detection, the ID images and OD images have very similar semantics. So at this case, yeah, the compatible condition may not hold. So we cannot achieve, that means we cannot achieve the optimal performance, or the performance may be not stable. So that is this theory tell us. Next, I will introduce another classical assumption in machine learning, which is called the realizability assumption, which means that we can always find a good predictor from the hypothesis space, such that the risk, the ID risk plus OD risk can achieve the best error 0. And the leading condition and the compatible condition are both necessary conditions. The realizability assumption can conclude the compatible condition, and the compatible condition can conclude the leading condition. So here, this graph shows and some assumptions such as the hyperspace is generalized by neural networks. And the realized assumption implies learnability, and the learnability implies a compatible condition, and the compatible condition implies the leading condition. And in fact, in some special distribution space, the leading condition can also imply the realizability assumption. So in a density-based space, in a space, which means the space consists of some distributions that can be represented as integral form, such as the DXI, the marginal distribution of ID, and the DXO, the marginal distribution of OD. DXI plus DXO can be represented as a density function under some fixed measure. And the real example is that DXI plus DXO is a mixture of truncated normal distributions with bounded expectation and variance. Here is an example that is the mixture of truncated normal distributions can form a density-based space. So we can prove that under mild conditions in a density-based space, the learnability, the compatible condition, and the leading condition and the realizability assumption, these 4 things, they are all equivalent. Hence, we can use the realizability assumption to distinguish whether generalized O detection can be learnable in a density-based distribution space. So the realizability assumption implies that a large size model may be necessary to achieve the learnability of generalized O detection. That means if we want to achieve a generalized well O detection model, then the model should be large enough. Okay, so let's discuss. Here, I will introduce some impossibility theories. If the linear conditions or the compatible conditions doesn't hold, then we can use this to develop some impossibility theorems. Here, I will show an example. For example, in the one-class novelty detection, if the model is based on neural networks, and there exists an overlap between ID and OD marginal distributions, DXI and DXO, and we want to ask, what will happen? So first, the one-class and the neural network-based model can tell us that the minimal ID risk and the minimal OD risk is 0. But the overlap tell us the alpha risk, the minimal alpha risk for some alpha can larger than 0. And these two results are conflicts with the linear condition. So the linear condition doesn't hold. That means the generalized O detection is not learnable in this case. And of course, so yeah, in a simple example, we have found that overlap may lead to the failure of O detection. So next, I want to ask if any distributions in a distribution space haven't any overlap between ID and OD distributions, then what will happen? So I propose a new distribution space, which is called a separate space D, which consists of all distributions where ID and OD distributions haven't any overlap. So if generalized OD detection is learnable in a separate space, then that means we can always find a tight boundary corresponding to the hypothesis space H to distinguish ID and OD distributions. Say this figure. Yeah, there are two figures. Yeah, and the red circles are the classification boundaries. The blue ball or circle, the orange ball or circle are the ID distributions with different labels. Then, yeah, we can, if OD detection is learnable in a separate space, we can find that tight boundary is red circles, which means if the data is inside a red circle, then the data is regarded as ID. If the data is outside the circle, then the data is regarded as OD. So can we achieve that? Unfortunately, the compatible condition indicates that when a hypothesis space has a finite complexity, such as a finite VC dimension or finite graph dimension, but the feature space is infinite, then the generalized O detection is not learnable in a separate space. And this solution tells us if we hope the generalized O detection is learnable in a separate space, then the hyperspace H should have infinite complexity, or the feature space should be finite. And in fact, to the deep neural networks with some proper activation functions, such as the rule functions, yeah, we can prove that these deep neural networks has finite complexity. So we can only assume that the feature space is finite. And we prove that in one class novelty detection and some very mild conditions, the generalized O detection is learnable in a separate space if and only if the features on the hypothesis space contains almost all predictors. In fact, this theory is a very strong theory, and I think it's a negative theory. Because if we want to achieve learnability of all detection in a separate space, our model should remember almost all data. Next, we can also show that in a separate space and some mild conditions in a one-class novelty detection cases, we can prove that there exists a hypothesis set H to ensure the learnability if and only if the finite feature space is sufficient and necessary conditions. And in the real-world applications, the image data size are from finite feature space. But as I have mentioned before, this result is very strong and even negative. It tells us if we want to achieve a perfect generalized OOD detection performance, then our model should be extremely large. Next, I discuss how to remove this condition, that is the finite feature space are removed. Then this is related to another topic of OOD detection, which is called Fang OOD detection. That is the supersize of ID and OOD distributions have a positive margin. And at this case, the condition finite feature space can be removed. And in fact, these results provides us related spots to some famous work, such as the out-of-distribution detection with deeper nearest neighborhoods. Yeah. Summary. We mainly discuss three conditions: the realizability assumption, the compatible condition, and the learning conditions, to study the learnability of generalized OOD detection in some practical distribution space. And by these conditions, we aim to know when generalized OOD detection can be successful. And our results have shown as follows. The learnability of generalized OOD detection is not distribution-free. And in a single distribution space, the generalized OOD detection is learnable if and only if the learning condition holds. In a compatible ID distribution space, the generalized OOD detection is learnable if and only if the compatible condition holds. And in a density-based space, the three conditions are equivalent, and they can all imply the learnability of OOD detection. And if the learning condition or the compatible condition doesn't hold, then we can use this to develop impossibility theorems. And this graph shows the relationship of realizability assumption, learnability, compatible condition, and the learning conditions under some weak, mild assumptions. And sometimes maybe we can use the realizability assumption to make some rough prediction whether the generalized OOD detection can be learnable in some cases. And here I will introduce our future study in OOD detection theory. I will study the learnability of OOD detection continually. And in the future, I want to answer for any distribution space and the hyperspace H with finite complexity, whether the compatible condition is a necessary and sufficient condition to learnability. And the second problem, I think, is the most important theoretical problem in OOD detection, is that how good a deep model should be to ensure a good OOD detection ability. I think that is a foundation issue in OOD detection. Thank you. Yeah, that's all.
Thank you very much, Dr. Zhen. So the floor is for the audience. If you have any questions, you can either speak up or write them, and I can read them afterwards.
Hi, Zhen. Thanks for this great talk. Yeah, I have a question about this paper. In this paper, you basically say that if we do the sample base, like we test if one sample is OOD or not, if we do this kind of task, we actually have some conditions, right? And we cannot do it without the conditions. And we might not learn a good OOD detection model if we cannot satisfy the conditions proposed in this paper. Yeah, so I'm wondering, can we consider to do the OD detection based on the batch level? Like we can test a lot of samples. If a lot of samples, they contain the OD detection samples, that might be easier for the OD detection. And maybe we don't need to consider many conditions in that case. If we consider, okay, we'll test a bunch of samples if they contain the OD sample. Yeah. If we change the task to this kind of task, it might be easier, and we don't need many conditions to ensure we can have reliable results. I want to know, like, do you have any opinion about this kind of thing?
Oh, okay. Thank you. Thank you for your question. And I think the batch based on detection issue, yeah, is deeply related to two sample test issue. And from the technical field, I think the batch based on detection is simple than the sample based on detection, right? And but the real problem I think I focus on is that whether, yeah, the batch based on detection, yeah, can be used some real world applications. That is what I'm interested in. Yeah, if we can find some cases or some scenarios, we can use the batch based on detection, then I think it's worth to be researched. Thank you.
Okay, thank you.
I had actually a question myself when you were mentioning the fact that for auto-distribution detection that is learnable in the finite ID distribution space, you mentioned the learning rate, and I was not sure what do you mean by that and how you define it.
Oh, you mean, okay, let me go back. Let's go back. Here, right?
Yes, exactly, these convergence rates.
Yeah, you mean how can we achieve that, right? Yeah.
Yeah, what does it mean actually, and how we can achieve it?
Okay, we prove this result into two steps. The first step, we prove that in a finite ID distribution space, we can construct an algorithm, yeah, to achieve this learning rate. Yeah, in a finite ID distribution space, that is ID distribution, yeah, only finite. The number of ID distribution only finite. And then I will use the property of compact. The property of compact, yeah, to discuss, yeah. In fact, a compactor mean always can be replaced by the finite, right? Yeah. So yeah, we use this to prove, yeah, two steps to prove it. And of course, in the process, when we have used some distribution discrepancy distance, yeah, to estimate the difference of different ID distributions. Use distribution discrepancy to distinguish different ID distributions. That is the key idea.
Okay, I see, thanks. And a follow-up question, you mentioned that here it's the case where we have finite ID data sets, but this is mostly the case in the real-world scenarios. I mean, in real-world scenarios, it's finite sets.
What you mean? You mean
when you design auto-distribution detection algorithm, we generally have finite ID datasets. That's what we have in the real world. I'm trying to take in a practical case, imagine that you are in computer vision. So the ID datasets are finite.
Yeah. Because the real issue is that we want to find an algorithm, yeah, from an algorithm space, yeah. So the key is how to distinguish different ID data sets, yeah, by some diffusion discrepancy. And if we can detect, we can identify the ID data size. That means we can, we can then, that means we have get all informations of the ID data size. So that's why here I use a finite. I use the finite.
Okay.
And then I will use the complex property to replace the finite property.
Thanks. Thank you. Any more questions? You can also write them in the chat if you prefer. Maybe one question about future work. I was wondering if you have an idea of some kind of robust statistics that can be used to study the robustness of auto distribution detection, because the fact that you have defined these theorems, these conditions, I was wondering if we can go from these hypotheses to actually statistics that can be used for the OOD detection.
Okay. You mean, we can we use a robust statistic to study OD, right?
Exactly. No? Yes.
Oh, okay. Yes. I think we can use a robust statistics to study OD detection, and in fact, I think have many people and researchers discuss these questions. And if we want to use a robust statistics to research OD, we need to give up the Packer theory framework. And in fact, the existing work mainly focus on some special distributions, such as the Gaussian distributions. They want to ask if there are some outliers in the Gaussian distribution, in samples of the Gaussian distribution, can we estimate the mean of the Gaussian accurately? So that is the robust statistics have done. And from my field, maybe in the future, we can borrow the idea of statistical robust to research or detection. I think it's a promising way.
If there are no more questions, we can close the session. And thank you again, Dr. Zhen, for the presentation, for the talk, and it was very fascinating. And for everyone, I also welcome you for next week's talk. We have a talk on the 16th of February about adversarial attack in black box settings. And thank you all for joining today. And I wish you a great day or evening, depending on the people.
Thank you.